You all tune your radios into frequencies in your car or somewhere. What unit do you have on your car for the radio, for a frequency? What is that? It's a hertz. Kilohertz sometimes, but it's a hertz, it's a frequency. 1/seconds is a hertz. I'm not going to use it that much right now, but when we start getting into more frequencies and oscillations later on, or we start talking about waves, then I might, for now, we'll just leave it in seconds so you don't get mixed up. But you might see it that way also. Not a whole lot. In the reading, I think you'll see more of it than the problems that I've chosen for homework and the ones that we do in class. Okay. So, understand what these mean, what they're giving you here in terms of their definitions. You can go back and forth between frequency and period by just taking the reciprocal of one or the other. Okay. So frequency is 1/period, or period is 1/frequency. Okay. Nothing else to it.
And then will that be unitless? Or will...
Frequency? 1/time, 1/seconds. Yeah.
Frequency is the number of revolutions per second.
So just be careful about using the period for your time. For one complete circle, if we're moving around in a circle, I could say that V is equal to 2 pi r over t. Because your 2 pi r is your distance around the circle, and your t is the time it takes to make one complete circle. In general, though, I could say that V is equal to just some distance over time. So it's only this capital T if you're going around the whole circle one time in the 2 pi r here. You could also rewrite this in terms of frequency, because 1/period is the frequency. But that t is only one specific time. Don't confuse that with some other time I give you the problem. If I say this is the time to make one complete revolution, if it's a circle, you can use something like that. Otherwise, it's just the t that we're going to see in all of our equations. Okay? So let's talk about now angular acceleration. And I'll define the average here for us first. This is just the rate of change of angular velocity. Just like regular acceleration, or what we call linear acceleration now, was just the rate of change of your velocity. It was how your velocity was changing. And we saw back with the linear velocity, that velocity could change by speeding up, slowing down, or changing direction. This has units of radians per second squared. The little bar up here means average for that equation right there. So let's just add on some more things over here to our list. Acceleration A has units of meters per second squared, and now alpha has units of radians per second squared. If the rotation is speeding up, then omega and alpha have the same sign. This works just the same way that linear velocity and acceleration did. If I was speeding up going that way, then my acceleration pointed that way. If I was moving that way and slowing down, then my acceleration pointed the opposite direction. Same idea here with your direction for the acceleration. Some of you may not have used this letter before. This is just an alpha for that angular acceleration. Make sure your alphas look like alphas and not A's. Sometimes people get lazy and their alphas look something like that, or they make this too small or something. You don't want to mix up an alpha with an A because we're going to have both in the same equation sometimes. So you have to be clear with your alphas. Some people say these look like just little fish here, and that's maybe how you may remember it. I hear a lot of people saying that. Some of you have kids, some of you might have that grammar school paper at home where you can practice writing all your letters. Practice writing your omegas and your alphas. We don't have upper or lower case, it's just these ones. But make sure you can write them clearly. You really don't want to get mixed up, and you don't want me getting mixed up when I grade your paper. Because if I can't understand it, then I won't give you points. Okay? You think I'm joking, but some people really do, after this class, they just spend a little bit of time rewriting these letters. And even thetas from the first day of class, some people kind of say, well, I didn't know how to write a theta. And they're kind of asking me, where do I start my theta? Practice for a little bit, get comfortable writing them. You're going to need to write these letters. You will need to write these for this little quiz on Tuesday. I'm going to ask you for things like this probably here. I want you to know all your letters that go with the linear or the angular variables. I want you to know all your units. These are all things that you'll have to be able to write down next time. Okay? This is part of the thing I was talking about with the notation and just the new language here, that I want to make sure that you're studying some over the weekend, because otherwise next week you'll just be behind. Okay? So that's our angular acceleration. We're not going to worry about any of the vector properties of that either. We just need to know here that the omega and the alpha have the same sign if we're speeding up. If we're slowing down, then they are the opposite sign. Okay? So let me draw another picture here and talk about some of the accelerations that we have. There's R, just to measure that. Let's just say here that we are speeding up. In the counterclockwise direction for this picture. So you can show on here, you can put the alpha like that. Just remember that when you show that little curled arrow, that's not representing a vector. It's just telling you the direction that you're speeding up in, or the direction that you're rotating in before when I put the omega on there. These vectors are really in that third dimension coming out or into the board, but we're not going to worry about that here. Okay. So now if we're speeding up, if our rotation is speeding up around like this, then we can also describe that with an alpha. Okay, to describe the angular acceleration. What other kinds of acceleration do we have here in this problem? If you have a circle here, something rotating, what other acceleration is there? One of these we already know. If you're moving in a circle, we always have an acceleration that points toward the center. Okay? So I'm just going to pick a point, say right here this time. And the point on my circle that I draw, these doesn't matter, I'm just going to choose up here. And say, at this point, we know we must have an AC that points toward the center of that circular path. We've learned that before. But before, we almost always just talked about uniform circular motion. What did uniform circular motion mean about the rotation? What did that tell me? We said it was uniform circular motion. What did that uniform word tell us?
Stayed the same.
It's constant. That we were moving around with constant speed. So we only had that acceleration, but we weren't speeding up as we're going around. Well, now this alpha tells me that we're speeding up as we're going around. So we could have had this, and we did have this acceleration all the time, by simply just moving around in a circle. That came from really the change in direction of our velocity vector. But now we're changing direction, and we're also speeding up as we go around. So if I was talking about this same point right here, and I'm speeding up going around in this counterclockwise direction, would there be an acceleration going around the circle? This way or this way? Imagine your car driving around the curve like this. I'm speeding up. If I'm speeding up, then my acceleration, my linear acceleration goes with or against my velocity for speeding up. With. So if my velocity went which way right here? That way. Then my acceleration is going to go that way. Okay? So this is what we call the tangential acceleration. We didn't have that before because we had uniform circular motion where the speed was not changing. Okay? So we didn't have this AT. But if we're speeding up, if we have this alpha now, then we have a tangential acceleration. Okay? So now there's two components here of acceleration. Okay? AT is equal to the tangential acceleration. Vt was equal to r omega. At is just equal to r times alpha. So if you have one, you can get to the other pretty easily as long as you know the radius of that path there. It's easy to go back and forth between the linear and the angular variables here. And just from these equations here that we saw for the Vt and now here for the At, the tangential acceleration here. Okay. We will see the same thing with the units one more time. That if you put your unit here of a meter in for that radius, and you put your unit here for alpha in as radians per second squared, you're going to get units of meters times radians per second squared. But this just has units of meters per second squared. Okay. Another time where you would just leave that radian off when we're going back and forth between the linear and the angular variables here. AC, we remember, is our centripetal acceleration. Anybody remember what that equation is? James, I think you know it.
Oh, I'm sure I don't.
There's a V in here. What else? There's an R. Does that look familiar at all?
Not really. It's been a while.
This is alphabet soup at this point.
Yeah, and that's part of what today will feel like, I think, because of all these things here. And this is the part that I really want to give you this quiz to look it over the weekend. And once you do it, you get comfortable with it. And it is for a while. And this is the part really with this part of the material in this next unit. Mistakes that happen with kinematics are usually mistakes because you're mixing up all these different variables. You don't know sometimes if you should call your A an A, AT, an AC, or an alpha. You put numbers in the wrong place. There's common mistakes that people make with just mixing up all the variables and not knowing how to translate the problem and take the numbers and then, do I know if I call that omega or a V? That's what I want you to start getting into over the weekend. It's just getting comfortable looking at all these new variables. Okay? So we have an AC and the AT. This was an old equation, but this is an equation that I do want you to have memorized for this test because we're going to be using it here in this unit. And for many of you, like you just said, it feels like it's new anyway. So let's treat this like a new equation and add it to our list here for this
No
unit.
problem there.
Okay. So we also have here, now you have two components of acceleration. Before, remember how we always chose our coordinate system to try to go with the acceleration? And then when I did that, I only had acceleration in the x or the y. When we were going down the incline, I just rotated my coordinate system so that one of my axes went with the a. We never had two different a's before. These two components here of the acceleration make up the total a, the full acceleration, which is just really a vector that does this. The AC and the AT combined is really just a vector that does something like this. That one we call a.